Now, when we have some metrics, balanced accuracy and F1, the question is, how do we select a model that's best, or how do we pick hyperparameters, for example, size of the model or settings of some coefficients that are not optimized on the training data directly, for instance, like parameters in a perceptron or a neural network. How do we even gauge how variable is the performance of our model? Basically, how do we measure anything given the data? And cross-validation is to the rescue. It's a technique that is extending our original approach to data split. Remember, we split the data initially into train and test. And test was basically holdout. We never used it to do anything with the model besides the final check. And there was something else, validation, which was useful for precisely hyperparameter optimization, not just learning, but controlling overfitting and things like that. But can we, well, this is still just one final number. This final number, performance on test, doesn't tell us anything about variability of that result. Because imagine we could have selected a different test and a different train set even from the same data as we have. So we could have selected this part and that part and randomly this part, say, all together to form our test set, or any other allocation of those subsets, right? Let's move it over here and we'll get another split. What if the performance by chance just totally change? What if in this particular split of the test we got 20% very hard examples and they never been present just by chance, right? They've never been present in the train data. So how do we deal with that? How do we avoid or cope with the situations where this could have happened? Or how do we know if it happened or not? So cross-validation is a technique that is to help. So our original data is this, everything. So what we do is we randomly reshuffle the data, just uniformly, randomly reshuffle the data. And then we split the data into what we call folds. And we split it into k folds. This example, this figure is for 5 folds, but it could be 10. Rule of thumb is usually do 10, but it really depends on the size of the data that you have, and it could be whatever. So k-fold cross-validation, that's how it's called. That's why in our specific case it is 5-fold cross-validation. So after splitting our dataset, the complete dataset available for us for training, imagine our goal is to select a better model out of the two. One model will be logistic regression, just to give you a concrete example. And another model will be a decision tree. We haven't covered decision trees in this class, but I'm assuming you're familiar with them. So what we do now, we have 5 folds, and correspondingly we have 5 splits. This is split 1, this is split 2, split 3, split 4, and split 5. What that means is we are sequentially take one of the folds and hold it out as a hold out fold. Notice 1 is missing in our training folds or training data, 2 is missing in our training data, in the split 3, 3 is missing, and so on and so forth. So the task now is to take our 2 models, 1 and 2, and train each on this complete training data. And then we'll produce model 1, which is logistic regression, and model 2, which is a decision tree, in model 2. After we trained those 2 models on this training set, we can compute our accuracy measure, which is either balanced accuracy or F1. Now we know better not to use accuracy anymore. So we can compute those 2 numbers, or one of them, depending on which one we choose. Or we can compute something else, which I will talk about in the next episode, in one of the next episodes, which is called area under the curve. So we have 2 numbers, one for each of the methods. Then we move on to this data set, or to this split, and train on new training data. It's now different. It excludes 2, but it includes 1. And again, we compute the performance of each model. Notice that model 1 and model 2 produced on split 1, and model 1 and model 2 trained on split 2 are slightly different, or maybe completely different, depending on which difficulty or what kind of difficulty problems were in the fold 1 and in the fold 2 that was included here but wasn't included here, and vice versa. So we repeat the process. You can do that whether you have 2 models or even 1 model. Imagine that your task is not to compare model 1 and model 2, but just assess the variability of your model with respect to the data. Is it consistent? Is it does it have high variance depending on data, or it's pretty much returning the same result? So after doing that, we can look at the results. Well, this is a result of a different cross-validation. In this example, as you see, it's a 10-fold cross-validation. And we see performance of logistic regression with the mean at 64, and we see performance of decision tree with the mean closer to 69, and we also see variability. So now we can select which model, which one of those models we want to select. So, but, well, which one to select? Number 1, number 2, like which one of the folds is the best model? Shall we select this model? But wait a second, it hasn't been trained on the complete data set. It has only been trained on a subset of the data that didn't include 10th fold, right? This is 10th split. So people from sklearn, let me go out of order, describe the following procedure. When we do our model selection, we leave some true holdout set. So after we do five-fold cross-validation. This is exactly equivalent to what I was describing. And from this five-fold cross-validation, we found, say, was it accuracy? Let's check. Well, accuracy, so bad. Let's assume it was balanced accuracy that we were looking at. And we have two models, logistic regression and decision tree. Decision tree, as you remember, gave us something around 69. We will be using our box plot here. And logistic regression gave us something around 64. The variability was about equal, if I recall correctly. Now what we do, we take this complete data set and retrain on the complete data set the winner decision tree. And then we report the winner's performance on test data. That's how we know what to expect in the wild. But cross-validation is not only a good technique, not ideal, by the way, there is no silver bullet. It can be cheated. You can overfeed to cross-validation. There are leakages to watch out. So, but anyways, it is a good technique. It is much better than testing and training, training and testing only on a single split. Because when you do that, you have no idea what's going on. You can't report much about your model. But another use for cross-validation is hyperparameter optimization. For example, shall we take two-layer neural network, one-layer neural network, or three-layer neural network? Shall we take 10 hidden units per layer? Shall we take 100 hidden units per layer? Shall we take 100 hidden units in the first layer and then 50 in the second? And all of those things are hyperparameters, the architecture of our model. This diagram from sklearn documentation describes how to a cross-validation process of choosing those best hyperparameters for the model and then returning the best model for using in production. So what you could do, you could say, okay, I have a few hyperparameters for simplicity, so I can draw it for you. Let's assume we have just one, hyperparameter 1 and hyperparameter 2. I will pre-select the values of hyperparameter 2 to consider. I have some reasons to believe that it will be H21, H22, H23, and H24 and H25. So if I predefine those, they could be anything that comes from my prior knowledge of the problem or my ignorance, pretty much. That's what people usually go with, but we'll try to avoid this in the future. And the same for H1. Let's move it out. We will select H11, H12, H13, and H14. What am I doing? H14 and say H15. In this particular instance, our data scientists happen to select equal number of parameters, equal number of values of each hyperparameter to try. That's what I should have said. So for each candidate for hyperparameter 1 and for each candidate for hyperparameter 2, we have a node here where they intersect. And regardless of the value of H1 H1, 1, H1, 2, and so on, those candidates, regardless of those values, we will have that grid. So hyperparameter search is traditionally called grid search for that reason, because we need to run a model for each intersection of hyperparameters, of hyperparameter values, or hyperparameter candidate values. So let's see how the same cross-validation procedure could be used for hyperparameter search. Now, when we've done our first split, and this is our test data, we will train on this training data all of our models that include all possible combinations for H1 and H2. So we will train 25 models here and test them on the holdout. Then again, we will train 25 models on this cyan or green color, greenish color, and test it on fault 2. Then from there, we will have our 25 models with all combinations of H1 and H2 candidates, and say we will have not only their means, average performance, as we decided, or as I decided, we will use balanced accuracy, but we will also have the spread. So technically we can see statistical significance of the difference between those values, and assume somewhere there is a candidate in this particular hyperparameter settings for H1 and H2. Our balanced accuracy is the highest. What do we do next? Well, we say, oh, this is the sweet spot. We'll fix those hyperparameters. That's our candidates. And with fixed values of those hyperparameters, we train a model that we can now test and see if it really performs well. And then off in production it goes. But let's go back to model selection. So now we have, say, logistic regression, decision tree, I don't know, random forest, multi-layer, perceptron, SVM, and lots and lots and lots of models. We need, via cross-validation, to select one of these models that perform best. In one of our previous lectures, I showed you AutoML tool. That is our homegrown tool. You can just pip install or Google it. It's multi-classifier. Just give it your training data, X and Y, where X is a matrix and Y is a vector, and it will run all of the classifiers for you, cross-validate it, and give you the result. But wait a second, which one of the SVMs we run, which kernel, which soft margin parameter? Because depending on which one we choose, we will get different accuracy. We will get totally different result. Some of them will be better, some of them will be worse. What if by chance, even when we're doing our cross-validation, we selected the support vector machine, with parameters that just not its best for this data. More interesting, right? MLP, how many layers, how many, what kind of nonlinearities, and all of those choices, right? And the same for any other model. So can't we do somehow better? Can't we select an optimal hyperparameter choice for each of these methods? But how do we do that? If we select hyperparameters on the same data that we're training in the cross-validation, then we will be overly optimistic. So traditional way, or recommended way actually, and very good in practice, is to repeat the hyperparameter search cross-validation inside of the loop of the main cross-validation. So when we have selected those training faults, test data, let's pretend now that we have a data set which is not this anymore, not that, but rather the smaller data set, and say we're working with support vector machine. We're doing whatever, depending on our data, 3-fold or 10-fold or some fold split, and repeat our hyperparameter search, hyperparameter optimization, the same way as I described in here. Then, for each fold, we select the best hyperparameters, or the best set of hyperparameters that is possible. And in the end, when we select the best model, we retrain it with the best set of hyperparameters. So that is nested cross-validation. And as this plot shows, again from my sklearn, is that if we don't do nested cross-validation, so our score on training data is higher because we're more optimistic. And when we do nested cross-validation, we're less optimistic, but we're still selecting, or more likely to select, the highest performing model. Oops. Sorry. Okay. So grid search, right? Again, what if we're in a situation like that, one of the parameters can give us super high performance and another parameter doesn't affect the performance as much, right? So anywhere we choose here along this line will get super high performance. If by doing our grid search for hyperparameter optimization, we just uniformly put the values on the grid as in this figure, then we will oversample the unimportant parameter, or, well, imagine that it's a hypercube, right? We need all possible combinations of the values. We will oversample this value, but by going uniformly on the important one, we will never be able to get to the maximum or the optimum value of hyperparameters. So there are lots of ways, various ways that are very complicated, Bayesian, Gaussian processes, and so on and so forth, more like active learning for hyperparameter optimization. Let's not consider that. In 2011, 2012, Bergstra and Benjo have shown that if you actually randomly sample the space of hyperparameters, then the chances of hitting that optimal point are higher. This guy. So this combination of H1 and H2 will give you the highest balanced accuracy. Or whatever metric you're trying to optimize, and the chances that you will find it are higher. So Lots of other enhancements since then exist, but I was surprised that not too many. Let's not cover that in this lecture. So there are tons of tools that will make your life easier, such as hyperopt, that is from the original author of the method that I've just shown. It includes the random search and other tricks on top of it when you're automatically optimizing your model. Hyperparameters again, not just parameters. And then there is Aptuna, a recent one, and Orion is something else, but it has tools for search. Let us click on them and see, just to give you an idea of how this look like. So this is hyperopt, distributed hyperparameter optimization. Yes, by the way, they're all distributed. They work with Apache Spark and Slurm clusters and so on and so forth. So random search, as I said, and then tree of parson estimators. Now you will be able to read this paper and the examples, because you know what is a parson estimator after our lectures. Again, Apache Spark based on MongoDB. Aptuna is a slightly more recent uh, and friendlier one, and easier to use, I guess, although the algorithms under the hood are similar. And it's all nicely pip install, and it'll let you, in a couple of lines, do hyperparameter optimization. Should be helpful for your class project. Orion, let me show you quickly, is quite a different beast, but it minimizes the effort for hyperparameter optimization as well as parameter optimization by making it all bash scripts with just one-liners, and also includes Bayesian hyperparameter optimization. So that's it for cross-validation for now, but the topic is very deep, lots of papers. If you want to dive into it and learn something useful for you, you're more than welcome to. There are lots of ways to get lost in the wealth of knowledge that is being accumulated by the people there. One last comment though, notice that statistics has existed for years, right? At least for 120, as far as I recall. And people knew that single point estimates are not the way to go. But imagine we just have one model and we want to do cross-validation for hyperparameter search. One model, couple of hyperparameters, a couple of values. Look, like how many evaluations or how many training runs of this model you need to do to perform in order to perform five-fold cross-validation. It's quadratic, right? It's about 35, I think, because you need to train on this train data, but then you need to train on the whole fold in the end. So it's multiple models, multiple retrainings, multiple comparisons. So that's very, very computationally intensive, and it only became possible relatively recently when we have, again, relative abundance of computational resources if you compare with statisticians of the past. Okay, so that's it for cross-validation.